Hello everyone, welcome to this lecture. So, in this lecture we will discuss perfectly secure verifiable secret sharing scheme, where we have less number of corrupt parties compared to the previous schemes, namely the number of corrupt parties is less than n over 4, and since the number of corrupt parties are less than the previous protocol. So, in the previous protocol the number of corrupt parties were up to n over 3, and that is why the verification process, namely to verify whether the dealer has shared consistent polynomials or not, was quite technical, right. It involves a lot of steps, but now what we will see in today's lecture is that if you have less number of corrupt parties, then the verification process becomes relatively simpler. So, for today's lecture we will consider first a 3 round protocol, okay, and then we will see that by using the round reducing technique which we had discussed in the previous lecture, we can bring down the number of rounds to 2 rounds. Okay. And this is clearly an improvement over the previous protocol, the previous verifiable secret sharing scheme, because in the previous VSS scheme the number of rounds were 5. So, you can see that you have a trade off. If you want to tolerate more number of corruptions, namely t less than n over 3, then the protocol required 5 rounds. Of course, we could reduce the number of rounds to 4 by using the round reducing technique, and we have not discussed, but we know that a minimum number of rounds required by any VSS scheme, perfectly secure VSS scheme with t less than n over 3 is 3 rounds. Whereas, what we are going to discuss today is a 2 round protocol with t less than n over 4. So, if you have a trade off between the number of faults which you can tolerate in the protocol and the number of rounds in the sharing phase. So, let us start with the sharing phase protocol. So, most of the steps of the sharing phase protocol remains the same as it was for the previous VSS scheme, where dealer embeds its secret in a random bivariate polynomial, and then it distributes the row and column polynomials to individual parties, and then the parties interact and verify whether the row and column polynomials of all honest parties lie on a single t degree bivariate polynomial. But now the steps become simpler compared to the previous VSS scheme. So, in the first round, dealer on having a secret S embeds it in a random t degree bivariate polynomial. For that, it first picks a random t degree summit sharing polynomial, and additionally t random univariate polynomials in x, each in variable x and each has degree t, and using this t plus 1 polynomials, namely the summit sharing polynomial and the t random univariate polynomials, it interpolates and gets a random t degree bivariate polynomial. And because of the way the secret is embedded in the bivariate polynomial, it holds that the constant term of the bivariate polynomial is the dealer's secret, which also happens to be the constant term of the summit sharing polynomial f of x. And since these polynomials f1x, f2f, ftx are picked randomly, and so is the summit sharing polynomial, it guarantees that the overall bivariate polynomial is a random t degree bivariate polynomial. It then hands over the ith row and ith column polynomial of this bivariate polynomial to the ith party, and then the rest of the protocol involves interaction among the parties to verify whether the dealer has distributed consistent row and column polynomials to all the honest parties, because if the dealer is corrupt, then it may not follow the protocol instructions. So, right now I am explaining the protocol without using the round reducing technique. At the end of the lecture, we will see that how we can reduce the number of rounds during the pairwise consistency check using the round reducing technique, which we had discussed in the earlier lecture. So, once the first round is over, then during the second round, every pair of parties exchange the supposedly common points on their respective polynomials. So, you have party pi and party pj with their respective row and column polynomials, and they exchange the supposedly common points on their respective row and column polynomials with each other over the private channel during the second round. So, for instance, Pi sends the value of its row polynomial evaluated at alpha j and the value of its column polynomial evaluated at alpha j to Pj. And in the same way, Pj sends the value of its row polynomial at alpha I and the value of its column polynomial at alpha I to Pi. And then ideally we expect that if dealer Pi and Pj are honest, then we expect that Aij should be equal to Bji, and we also expect that Bij should be equal to Aji. Ideally this should be the case if dealer Pi and Pj are honest. So, during the third round, the parties after performing the pairwise consistency check announces the results of the pairwise consistency checks publicly. So, that involves the usage of broadcast channel. So, Pi says that it is fine or okay with j if the pairwise consistency passes, if it is positive, otherwise it sends an NOK message against Pj, that means it is in dispute with Pj. And similarly, Pj also after performing the pairwise consistency check either broadcasts an OK message or an NOK message indicating that it is in a dispute with Pi. Now, we have already utilized 3 rounds. Now, based on the results of the pairwise consistency checks which are publicly available. Why they are publicly available? Because all these OK and NOK messages are made public using the broadcast channel, and anything which has been made public using the broadcast channel will be received identically by all the honest parties. So, at the end of the third round, all the parties will know whether party Pi is in dispute with Pj or not, and vice versa for every pair of parties Pi Pj. Now, based on these results, the parties identified a set of happy and unhappy parties as follows. So, the parties construct a consistency graph where the vertices are the parties themselves. So, there will be a node representing party P1, there will be a node representing party P2, there will be a node representing party Pi, there will be a node representing party Pj, and so on. Okay. So, there will be n nodes in the vertex in the graph, and the edge set in this consistency graph will be as follows. So, there will be an edge between the nodes representing the parties Pi and Pj if and only if both of them are okay with each other. That means, neither Pi is in dispute with Pj nor Pj is in dispute with Pi. If that is the case, then there will be an edge between the nodes representing Pi and Pj in the graph, otherwise there will not be any edge between the nodes representing Pi and Pj. Now, notice that this graph, this consistency graph will be common. That means, all the parties will be constructing the same consistency graph. That means, it will not be the case that if, say for instance, P1 has added an edge between Pi and Pj in its copy of the consistency graph, then P2 is not adding that edge, because these edges are added based on the OK and NOK messages which are publicly available. Okay. Now, let us make some claims regarding the properties of this consistency graph. So, the first property is that if we consider a pair of parties Pi and Pj who are honest, and if there is an edge involving the nodes Pi and Pj in the consistency graph, then their polynomials are pairwise consistent. Okay. This is because the edge between Pi and Pj is added only when Pi has broadcasted an OK message for Pj and when Pj has broadcasted an OK message for Pi. And why these parties would have broadcasted OK messages for each other? Only after verifying that the pairwise consistency test is positive for Pi and Pj individually, which automatically implies that their polynomials, the row and column polynomials, are pairwise consistent. Okay. Now, based on this claim, the parties identify the set of happy and unhappy parties as follows. So, the set of happy parties is defined to be the parties in the maximum sized clique in the graph G. Okay. So, what is a clique? It is a complete graph. So, the parties once they construct a consistency graph, they try to find out the maximum sized complete graph in that consistency graph, and the parties representing the corresponding nodes constitute the happy set of parties H, and the remaining parties who are not part of that clique, maximum sized clique, is said to be the set of unhappy parties. Okay. Now, the first sanity check which we make here in the protocol is the following. If we see that the number of unhappy parties is more than T, then it automatically implies that the dealer is corrupt because of this claim, and so it is safe to discard the dealer, and discard the dealer means terminate the sharing phase protocol here itself and assume that dealer wanted to share the value 0 and everyone takes a default share 0 on the behalf of the dealer. Now, why this sanity check makes sense here? Because if the dealer is honest, then all the honest parties in the system will be pairwise consistent because of this claim, because dealer will be giving consistent row and column polynomials to all the honest parties, and as a result of that the pairwise consistency check between every pair of honest parties will be positive. They will be broadcasting OK messages for each other, and how many honest parties are guaranteed to be in the system? At least n minus t. That means there could be up to t corrupt parties who may unnecessarily broadcast an NOK message against an honest parties. Okay. So, how many that means what could be the maximum number of unhappy parties if the dealer is honest? Well, no honest party will be unhappy if the dealer is honest. Only the potentially corrupt parties can be unhappy, and how many corrupt parties are there in the system? There are up to t corrupt parties. So, that is why the cardinality of the set of unhappy parties for an honest dealer will be at most t. It never crosses t, and that is why an honest dealer will never get discarded because of this sanity check. That shows that if at all the number of unhappy parties is more than t, then definitely the dealer is corrupt, and so it is safe to discard the dealer. Right. So, now based on this sanity check, let us make the second claim here. We claim here that if the dealer is not discarded, and we have already argued that an honest dealer is definitely not getting discarded, then we claim here that the polynomials of all the happy and honest parties lie on a single t degree bivariate polynomial. Call that bivariate polynomial as f star x y. And what do I mean by saying that the polynomials of all the honest parties lie on this bivariate polynomial? That means, if I take an honest happy party pi, then its x univariate polynomials lies on this f star bivariate polynomial. That means, its this f I of x polynomial is the value of the bivariate polynomial f star at y equal to alpha I, and similarly the y univariate polynomial which pi has received from the dealer also lies on the bivariate polynomial f star. Moreover, this polynomial f star will be same as f of x y if the dealer is honest, because an honest dealer distributes row and column polynomials lying on f of x y. And we have already argued that an honest dealer is never discarded in the protocol, and for the honest dealer the polynomials, the row and column polynomials of all the happy and honest parties will lie on f of x y, namely the polynomial selected by the dealer itself. So, now let us prove this claim. Why this claim is correct? Well, this claim is correct because if the dealer is not discarded, then we know that there are at most t unhappy parties. That means, there are at least n minus t parties in the happy set, and up to t parties in the happy set might be corrupt. Fine. So, that means, if I focus on the happy parties who are also honest, then they are at least n minus 2t in number, and n minus 2t is clearly greater than 2t, because we are working with the condition n greater than 4t. That means, we have at least 2t plus 1 happy parties in the we have at least 2t plus 1 parties who are happy and who are honest, and whose polynomials are pairwise consistent because of this claim. So, now we can trigger the pairwise consistency lemma and conclude that the row and column polynomials of all the happy and honest parties together lie on a single bivariate polynomial f star of x y. Now, the protocol is over, in the sense that we have no more rounds involved required in the protocol. If the dealer is not discarded, that means the verification is done, and what is left now is to compute the shares for the respective parties. So, how the shares are computed? So, depending upon whether a party is a part of the happy set or not, the shares are computed differently. If a party pi is part of the happy set, then it simply takes the constant term of the column polynomial which it has received from the dealer during the first round as its share. Whereas, if the party pi is not part of the happy set, that means it is not part of the clique, maximum sized clique in the consistency graph, then it has to do something else to get its share. What it does is the following: it simply ignores the column polynomial which it has received during the first round from the dealer, and it now recomputes its column polynomial. So, the recomputed column polynomial is also denoted by g I of y. So, the previous g I of y which it has received from the dealer during round 1 is ignored, and it computes a new g I of y as follows. And once it computes the new g I y polynomial, it takes the constant term of that polynomial as its share. So, now let us see how this new g I y polynomial or the new column polynomial is computed. So, during the second round, as part of the pairwise consistency check, this party pi who is not part of the happy set would have received the common values, the supposedly common values from different parties pj, okay, during the second round. So, it would have received the value aji from different parties pj during the second round as part of the pairwise consistency check. It focuses only on the aji values received from the happy parties. Okay, so, during the second round it would have received the supposedly common value aji from all the n parties. What we are saying here is that among those aji values, take only the aji values, the common values which have been received from the happy parties, and the happy parties are now identified, right. It has been identified at the end of third round. So, it may not be the case that all the parties are happy, some parties might be unhappy. So, for the unhappy parties, whatever common points you have received during the second round, ignore them, focus just on the aji values, the common values which pi would have received during second round from the happy parties, and then it applies the Reed-Solomon error correction and try to get a t degree polynomial, and we will show it will get a t degree polynomial. That t degree polynomial which it obtains by applying the Reed-Solomon error correction on this common aji values received during round 2 is taken as the recomputed column polynomial by pi, and as I said earlier, the constant term of this recomputed polynomial is taken as the share by party pi. Now, what we are going to claim here is that if there is some unhappy honest party pi, then as per this process of computing the shares, it will be recomputing its column polynomial g I of y. We are claiming here that this recomputed column polynomial g I of y is nothing but a column polynomial on this bivariate polynomial f star defined by the polynomials of the happy honest parties. That means, through this recomputation process, whatever pi is computing, whatever column polynomial is computing, it is not an arbitrary column polynomial. It is actually a column polynomial lying on this bivariate polynomial f star, which is defined or which is guaranteed to exist because of the pairwise consistency check of between the column and the row polynomials of the happy honest parties. So, let us prove this claim. So, how this recomputed polynomial is computed here? So, this recomputed polynomial is obtained by applying the Reed-Solomon error correction process. So, imagine that there are different parties p j. So, say p j 1, p j 2, p j k number of p j parties are there in the happy set, and they would have sent the common points on their column polynomials, the common points on their respective row polynomials to party p I. Now, among all these parties in the happy set who would have sent the common points on their respective row polynomials to p I during round 2, at least 2t plus 1 are guaranteed to be honest. Why so? Because the cardinality of the happy set is at least n minus t. That means, the cardinality of the happy set is at least 3t plus 1, and the common points on the row polynomials of all the honest parties in this happy set, it uniquely determines this column polynomial f star alpha I y. And what is the degree of this column polynomial f star alpha I y? It is a t degree polynomial. Now, there could be up to t corrupt parties in the happy set who during the second round might have given incorrect common points to p I, and it is precisely those points which are error corrected through this Reed-Solomon error correction process. So, it is not guaranteed that every party in the happy set would have given the correct point on its row polynomial to p I during the second round. The honest parties would have given the right points on their respective row polynomials to p I, but the corrupt parties might have given incorrect points to p I. There could be up to t such incorrect points, but there are at least 2t plus 1 correct points, and overall the degree of this f star alpha I y polynomial is t. So, now we know that if the degree of the polynomial is t and there are at least 3t plus 1 values of which up to t could be corrupt, the Reed-Solomon error correction process will work correctly, and whatever polynomial is obtained by p I, namely this recomputed g I y polynomial, it will be nothing but the supposedly ith column polynomial on this f star bivariate polynomial. That also shows that whatever share is computed by p I because of this second case is nothing but a valid share. We will prove that very soon. Okay. So, these are the 4 claims with respect to this sharing phase protocol, and now you can see that the sharing phase protocol is relatively simpler here compared to the previous VSS scheme. Dealer distribute the polynomials, parties perform the pairwise consistency check, make the result public, and that is all. We are not asking the dealer to resolve the polynomials of the unhappy parties, which was happening in the previous protocol. The unhappy parties, they are automatically going to recompute their column polynomials by applying a Reed-Solomon error correction process. Now, you might be wondering that why this recomputation may not work for the previous VSS scheme with n greater than 3t. Well, I leave it as an exercise for you. You can go through the analysis that we are doing in this lecture, and then you can see that where that analysis fails for the previous protocol. That means, why this protocol will fail with n greater than 3t, you can verify that, why it works with n greater than 4t. So, now let us prove the properties of the VSS for this VSS scheme, namely the privacy, correctness and a strong commitment. For privacy, we have to consider an honest dealer, and we want to show that if the dealer is honest during the sharing phase, then the view of the adversary remains independent of the dealer's secret, and the proof for this more or less remains the same as it was for the previous VSS scheme. Namely, what exactly the T corrupt parties receive in this protocol, what exactly is their view? Their view is basically limited to up to T number of row and column polynomials, nothing more than that. And these T row and column polynomials lie on a random T degree bivariate polynomial. So, we can now apply the privacy lemma, we can trigger the privacy lemma here, which says that if there is a random T degree bivariate polynomial, then the probability distribution of any number of any T number of row and column polynomials is independent of the constant term of the bivariate polynomial, and that guarantees the privacy here. Let us prove next the correctness property, for which again we have to consider an honest dealer, and we want to show here that if the dealer is honest, then there exists a T degree sum sharing polynomial such that every honest party outputs a share which is the value of that sum sharing polynomial at alpha I. Now, you can see there are two different ways by which a party would have computed its share. So, if the party Pi is a part of the happy set, then what exactly is the share of that party Pi? Well, it is the constant term of the column polynomial which that party would have received from the dealer during round 1. And now, because of the way dealer would have embedded the sum sharing polynomial in the bivariate polynomial, it follows that the constant term of the column polynomial GIY is nothing but the value of the sum sharing polynomial at x equal to alpha I. Whereas, it could be possible that there is an honest party Pi who is not a part of the maximum sized clique, that means it is not a part of the happy set, in which case the party would have recomputed its column polynomial and output the constant term of that recomputed polynomial as its share, but we have already proved in claim 4 that even the recomputed polynomial is going to lie on the bivariate polynomial f star as defined by the polynomials of the happy honest parties, and for the case of the honest dealer, the polynomial f star defined by the polynomials of the happy honest parties is same as the polynomial f of x y, which automatically shows that the recomputed polynomial g I of y is going to be the same g I of y polynomial which Pi would have received from the honest dealer during the first round. Now, you might be wondering, if the dealer is honest, why Pi is again recomputing its polynomial if it is not a part of the happy set? Well, Pi would not know actually whether the dealer is honest or corrupt. It has to follow the protocol steps, and what we are guaranteeing here is that even if the Pi is recomputing its column polynomial, for the case when dealer is honest, its recomputed polynomial will end up to be the same polynomial, same column polynomial which it would have received from the dealer during the first round. So, that automatically shows that even for the parties who output or who set their shares based on the recomputed column polynomials, their shares are basically lying on this sum sharing polynomial f of x. So, that completes the correctness property. Now, let us see the strong commitment property, for which we have to consider a potentially corrupt dealer, and for a potentially corrupt dealer we want to show that there exists some T degree polynomial such that the share of every honest party is going to lie on that sum sharing polynomial. And again, there are two possible cases depending upon whether the dealer is discarded of this because of the sanity check or not. If the dealer is discarded, then well, strong commitment is guaranteed, because in that case we can take the sum sharing polynomial to be the constant 0 polynomial, which guarantees that the share of every honest party is 0. Whereas, if the dealer is not discarded, then because of this claim 2 and claim 4, we know that there exists some T degree bivariate polynomial f star such that the column polynomials of all honest parties at the end of third round is going to are going to lie on that f star x y bivariate polynomial, right, and that is because of the claim 2 and claim 4. Now, let us take the Samir sharing polynomial f of x to be the value of this defined bivariate polynomial at y equal to 0. So, this f of x is actually a t degree polynomial because f star is a t degree bivariate polynomial, and now it is easy to see that irrespective of whether the party pi, an honest party pi, is happy or unhappy, the share computed by it is nothing but the value of this defined Samir sharing polynomial at x equal to alpha I, which implies that the strong commitment property is satisfied. Okay. So, we are now done with the 3 round VSS scheme, but I promised you that we will see that this protocol actually requires 2 rounds. So, what we can do is we can reduce the number of rounds to 2 by applying the round reducing technique. So, what we are going to do is the protocol remains more or less same, but in the first round parties will pre-exchange some random pads for OTP, which simplifies the pairwise consistency check during the second round. Namely, during the first round between every pair of parties pi and pj, they will exchange among themselves random OTP pads, and then during the second round these random OTP pads are used to make public OTP encryptions of the supposedly common points. Now, since the pads are exchanged privately between pi and pj, even if these OTP encryptions are made public, nothing is going to be learned about the individual values of the row and column polynomials of an honest pi and honest pj if dealer is honest. Whereas, if the dealer is corrupt, it will not be knowing beforehand what are the pads which have been exchanged between pi and pj, and that implies that if dealer has given inconsistent polynomials to pi and pj, then the OTP encryptions will mismatch and there will be a conflict between pi and pj. Now, how do we identify the happy and unhappy parties here? Well, the construction of the consistency graph remains the same, namely we will have n nodes representing the n parties, and now there will be an edge between pi and pj if their OTP encryptions are consistent, otherwise there will not be any edge. And then we take the happy parties to be the parties in the maximum size clique and so on, and share computation happens as it was happening earlier. Okay. Similar in the same way. Namely, if there would have been a party pi who is not part of the happy set, then it needs to find out the common values on its column polynomial which it would have received from the parties in the happy set. So, what it can do is that each party in the happy set, if there is a party pj in the happy set, it would have made public the value dji, and mji would have been received by pi. So, what pi can do is it can set aji to be dji minus mji, and then on this aji values it can apply the Reed-Solomon error correction as it was doing earlier and try to recompute its column polynomial gi of y. So, rest of the details remains the same. So, the 2 round protocol which I had discussed today is taken from this paper, and if you want to know more about perfectly secure verifiable secret sharing schemes, you can refer to this survey paper. Thank you.